This video begins our transition from examining individual scores to focusing on group averages. It does so by introducing the sampling distribution of the mean and the standard error of the mean. We previously used a single score for a person, or a rhino, and the standard deviation for a variable as a way to determine how large something is. We're now basically going to do the exact same thing, but instead of using a single score, we're going to be using a sample mean. And because we're looking at means, we don't want to just use the standard deviation that reflected the variability of individual scores. We need to know the standard deviation for means. This brings us to the sampling distribution of the mean. Let's say I'm looking at SAT scores, and we'll assume the mean SAT score is 1,000, and the standard deviation is 200, and the scores follow the normal curve. Now, we know this isn't quite correct, but later it will make the math more transparent and easier to see what's going on. Here's what the distribution of individual scores would look like. This black curve reflects a normal distribution with a standard deviation of 200 and a mean of 1,000. Thinking back to our normal curve video, just under 32% of the scores, or 32% of the individual students, are below 800 or above 1,200. Now, let's say that instead of looking at the distribution for individual students, I want to look at the distribution for the averages of groups of 25 students. So I go out and randomly sample 25 students and calculate their mean SAT score. And you go out and sample 25 students and calculate the mean for that group. And someone else samples 25 students and calculates the mean for that group. And so on until we have an infinite number of samples of 25 students and an infinite number of means for those samples. We then go and plot these infinite number of sample averages. What do you think that graph will look like? Okay, now pause the video and think about it logically for a moment. Don't worry about the math, okay? Start up the video when you have an idea. Here's the distribution for individual scores. Again, it really just reflects the standard deviation. And here is the distribution we would find for means of groups of 25 students. Notice the means are more clustered together. The standard deviation for the averages is smaller than the standard deviation for the individual scores. Now, if you didn't see that coming, think about it. It kind of makes sense. When I look at individual scores, I'll get a lot of students right around 1,000, but there'll be the occasional 1,400 or 1,600, as well as the occasional 600 and 400. Because the standard deviation is based on individual scores, they all show up and are all equal parts of that distribution. But when I sample 25 students, I may still get that student with a 1,500 SAT, but there are 24 more students, and some of them will have low SAT scores. When we calculate the mean, the high scores and the low scores will to some degree have an opportunity to cancel out, and as a result, the means for the groups will be more clustered together than the standard deviation, which is based on individual scores. So while we had nearly a third of the individual students with scores either below 800 or above 1,200, when we look at means for groups of 25 students, there are virtually no groups with means in that range. In fact, there are almost no groups with means below 900 or above 1,100. Now, what would it look like if instead of 25 students, we had means for samples of only 4 students? What would that distribution look like? Again, let's pause the video for a moment and see if we can figure it out. This green distribution reflects what we would see if we plotted means for an infinite number of samples of only 4 students. Notice that the means are still more tightly clustered together than the standard deviation based on individual scores. But now with only 4 students, there's less of a chance for high or low scores to cancel out, so the means are not as tightly clustered together as they were with samples of 25. One more sample size and then we'll move on. What if instead we had a sample size of 100 students? What would that distribution look like? In that case, the red distribution reflects what we would see if we plotted means for an infinite number of samples of 100 students. Means are now even more tightly clustered. But, and this is important, regardless of the sample size, the sampling distribution of the mean is always centered on mu, the population average. In this case, notice they're always centered on a score of 1,000. Now, the language I've been using can get a little cumbersome at times. We have the standard deviation, which is the standard deviation of individual scores. It's how spread out the individual scores are. But then we also have the standard deviation of sample means, or how spread out sample means would be if we had an infinite number of different samples the same size. So to keep things clear, we call the standard deviation of means the standard error of the mean. But it's just like a standard deviation. When we talk about the standard error of the mean, it is the standard deviation that we would expect to see if we had an infinite number of samples and an infinite number of means. Now, notice that in these examples we've just gone through, we pretended to have an infinite number of samples of 4 students, or an infinite number of samples of 25 students, or an infinite number of samples of 100 students. But we can't actually collect an infinite number of samples in order to calculate the standard deviation of those means. I mean, to calculate the standard error of the mean. How many samples do we really need to do this? 1. Yes, based on just 1 sample and 1 sample mean, we can estimate the standard deviation of means that we would actually see if we had an infinite number of samples of that same size. This is where it seems kind of like magic, which is why I'm wearing my Mickey Wizard hat. But we don't need an infinite number of samples. We can do it with the 1 sample that we have. So, how does it work? Well, when we know the population standard deviation, the notation for the standard error of the mean is sigma x bar. Let's pause here for a moment. Notice the sigma in sigma x bar. Remember, sigma is our notation for a population standard deviation. But here we've added an x bar as a subscript. Why would we do that? Well, it's to clarify that we're talking about the standard deviation of means. If you want proof that the standard error of the mean is just like a standard deviation, you see it right here. The notation for the standard error is sigma x bar. So if we know the population standard deviation, the standard error is equal to the standard deviation of our variable, sigma, divided by the square root of the sample size, n. Again, notice that we're calculating this based just on the standard deviation sigma. We're not actually going out and collecting an infinite number of sample after sample after samples. Now, what if we don't know the population standard deviation sigma? What then? Well, I'm jumping a little bit ahead of ourselves, but for me, this is where the statistical magic really kicks in. Well, it's the same thing. In later videos, we'll see that we just use our estimate of the population standard deviation. Remember, that's the lowercase s, our inferential statistics standard deviation, that we use to estimate the population standard deviation. Again, remember, we've talked about this, but we haven't calculated it yet. We're getting to that after a couple more topics. I just wanted to jump ahead here a bit and point this out so that you don't think that we can only do this because we know sigma, because we know the population standard deviation. We can also estimate the standard error of the mean based on our estimate of the population standard deviation that we calculate from our sample. But I digress. Let's take a closer look at the standard error formula and do a little mental exercise. What happens if I calculate the standard error based on a sample size of 1? Samples that contain only a single individual. The standard error of the mean is then the standard deviation divided by the square root of 1, which is just another way of saying that the standard error is equal to the standard deviation when it's based on samples of one person. That makes sense, doesn't it? The standard deviation is how spread out individual scores are, and samples of one person are just a bunch of individuals, so it's the same thing. But as the sample size increases, the standard error of the mean, the standard deviation we would find if we took averages for an infinite number of samples of that same size, will get smaller. This is another important point. For samples greater than n equals 1, the standard error of the mean is always less than the standard deviation, and it gets smaller as n increases. Now, that square root of n in the denominator for the standard error of the mean formula is a big deal.
It's not just big, it's huge!
This is why we like large sample sizes. Because as we'll see later on, it means, no pun intended, that with larger samples, it's easier to see things. For now, you can think of it this way. When we have an individual score, we use the standard deviation as our yardstick to measure just how big it was. We do the exact same thing with sample averages, but now we use the standard error of the mean instead, because the standard error is the standard deviation for the averages. Look at the formula. As the sample size gets larger, what's going to happen? Well, the denominator is going to get bigger. And as the denominator gets bigger, the standard error of the mean gets smaller. Our yardstick is going to get smaller. It's like you've shrunken your measuring tape. And if you shrink your yardstick, an average 5'9" guy like me can look like a giant. It's true when we're measuring effects in research as well. Let's pretend that this blue box represents some effect. Maybe we found that the class average test score is 8 points higher following some intervention. The size of the box reflects how big the effect is. And here's our yardstick that we're using to measure if this effect is large or small, given what we might have expected randomly. It's related to our standard error of the mean. Notice that as the yardstick shrinks, the effect doesn't get bigger, but it seems bigger relative to what we're using to measure it. As we'll see later, it becomes larger in a statistical sense, a statistical way that makes it stand out and allows the researcher to say, aha, I think I found something. Okay? This wraps up our discussion of the sampling distribution of the mean and the standard error. If you're interested, there are other related topics on other videos that you might find interesting, such as the central limit theorem. Okay? Take care.
It's not just big, it's huge.